So we're doing Chapter 5, Section 2, Day 2. We're going to verify trig identities, starting with example 7, continuation of the last, as of yesterday. So here we have cosecant theta plus cotangent theta times cosecant theta minus cotangent theta. So we have two binomials being multiplied together. In the previous example, we had to actually multiply them all the way out because they weren't the same. It was 4 different terms. This time, the first term of each is the same. The second term of each is the same. One's positive and one's negative. So this is what you would do if you or this is the result you would get if you factored using difference of squares. And if you can recognize the pattern, then you don't have to multiply it all the way out. You can just do that pattern in reverse. This is what I'm going to do. If you don't recognize the pattern and you just multiply it out using your box method or your FOIL method or whichever method you use to multiply binomials, you'll still get the same result. So it doesn't matter. It's just a little shortcut. If you recognize one's positive, one's negative, the first piece is matched, the second piece is matched. In that case, you can say this is the result of difference of squares. So I'm going to do it backwards, where I just take the first term. If it was squared, that would be the first piece. Difference of squares, difference means subtraction, so subtraction. And then the second one is squared, so cotangent squared. So this only works in this very specific situation. Okay, this is not multiplying them out. This is because the first piece is the same and the second piece is the same. And it equals whatever's on the right. Because remember, when we're verifying identities, we only change one side, the more complicated side. All right, so then I look at this and I'm like, I have a function squared and a plus or minus sign. This is probably going to be Pythagorean theorem. So the way I've been doing Pythagorean theorem is I need to make it match this exactly. So I go to my formula sheet and I find in the Pythagorean section, the version that has cosecant squared and cotangent squared in it. So the Pythagorean identity on the sheet says 1 plus cotangent squared theta equals cosecant squared theta. And I need to make it match because right now it's not matching. In my problem, cosecant and cotangent are together. So that means I need this cotangent to move over to the right-hand side, so I subtract it. So then I have 1 equals cosecant squared theta minus cotangent squared theta. Because I just subtract the cotangent squared over to the other side, and now I have this. And the right-hand side of the identity matches what I have in the problem. So that means I can take it out of my problem. I can take it out because it matches this side. And then the other side, this 1, I can put that in its place. So now I have 1 equals whatever's on the right. And what is on the right? A 1. So just bring that down. It didn't change. And I have verified 1 equals 1. Yes. So that was a pretty straightforward, easy example. All right, so example 8. This one is tangent x plus cotangent x minus secant x cosecant x equals 0. Okay, so as I start, the same way I start all of these problems is I start by looking at my formula sheet and seeing are there any identities that match. Well, the only 3 we've gone over are the cofunction, which always has a pi over 2 minus theta in it, and that is not in here. There's no pi over 2's anywhere. we've done the even odd identity, but I don't see any negative thetas or negative x's in here. So I'm not going to use that. And Pythagorean identity. I don't see anything squared. So probably not going to use that one. Then the basic ones were the tangent quotient identities and the basic reciprocals. So I'll go ahead and use those and turn everything into a fraction. Make everything sines and cosines. So tangent is sine x over cosine x. A plus sign stays a plus sign. Cotangent is going to be cosine over sine. Minus sign stays a minus sign. Here I have two functions being multiplied together, so I'm going to use parentheses. Secant x is 1 over cosine. Cosecant x is 1 over sine. And this is going to equal whatever is on the right, but because I don't want to be tempted to change what's on the right, I'm just leaving it blank and just writing equals. All right, so now I look at this again, and I see I have two fractions I need to multiply together. So I'm going to leave these first two the way they are, because I can't combine them yet because they're not the same denominator. I'm just going to leave them alone and rewrite them. So I have sine x over cosine x plus cosine x over sine x minus, and here I'm going to multiply, so numerator is 1 times 1, so that's 1. Denominator is cosine times sine, so cosine sine. So even these little steps like that, you want to do every tiny step when you're verifying, because you're showing 100% what you're doing. This is all about showing your steps. Okay, so now I have three fractions, and I want to add them and subtract them. We add and subtract fractions. We must have a common denominator. So we want to match the most complicated denominator, which would be the cosine sine. Because that way I only have to change two of them. So if in the first fraction I have a denominator cosine, this one's cosine sine, so it's missing the sine. So all I need to do to make this a common denominator is multiply top and bottom by sine x. Then I look at the middle one, cosine over sine. So I have the sine, but I don't have the cosine. So I need to multiply this one top and bottom by cosine x. And then the third one is cosine sine, so I don't need to multiply that one by anything. All right, so now I'm going to multiply them. When I multiply them, I see I get sine cosine, cosine sine, cosine sine. So I could say they're all cosine sine, because it's this one. It doesn't matter if I say sine cosine or cosine sine. That's the same thing. So now I'm going to have a common denominator. So I'm going to make it one single common denominator of cosine x, sine x. And the numerator is going to be what I get when I multiply these. So first one I have sine x times sine x. That is sine squared x. Plus cosine x times cosine x is cosine squared x. I didn't multiply the third one, so it's just minus 1. And it's going to equal whatever is on the right. Okay. So as I was writing sine squared x plus cosine squared x, it made me think of the Pythagorean identity. So I want to look at my formula sheet and see, do I have a Pythagorean identity that looks like that? I do. The Pythagorean identity is sine squared theta plus cosine squared theta equals 1. So what I have in my problem, sine squared x plus cosine squared x, that matches the left side of my identity exactly without having to rearrange anything. So that means I can bring that out of my problem. And So the matching part I'm removing, and whatever's on the other side is what I'm putting in its place. So all of that is just 1. So this is 1, and then I have -1. And then on the denominator, I have cosine x sine x. And this should equal whatever's on the right. All right, so now I have a single denominator, and in the numerator, I have 1 minus 1. 1 minus 1 is 0. I'll go ahead and write it out. So 0 over cosine x sine x. What is 0 divided by anything? Yeah, it's just 0. And it equals whatever's on the right, equals whatever's on the right, and what was on the right, it was 0. All the way down, it stayed 0. 0 equals 0. So I verified this to be true. Okay. One more example for you guys. There it is. We have tangent x plus cotangent x in the numerator and secant x, cosecant x in the denominator. And it should equal 1. So, same way I started the last identity, or the last problem I should say, was to look, see, is there an identity that I could use? Does anything match my formula sheet? No. Not really. So when nothing matches up, you can make everything sines and cosines. So I'll do that, because that's really the only thing I see to do, is make everything sines and cosines. And if you do a problem different than how I do the problem, and you still get that it's verified, that's fine. Like, this is just the way I see to do this problem. It does not mean it's the only way. So when I turn things into sines and cosines, I normally like to put parentheses around everything I'm changing, just to help me keep track. Here I see I have 4 items that I'm changing. I'm turning tangent x into sine x over cosine x. There's a plus sign. I'm going to turn cotangent x into cosine over sine. And that takes care of the numerator. So then, when I have fractions inside of fractions, I like to make my main fraction bar really big, just to make sure I keep it all separate so it stands out. It goes a little further to the left and the right than the others. That's just my way of doing that. Secant x is 1 over cosine times cosecant. So I want to put parentheses around those so I know I'm multiplying them. Cosecant x is 1 over sine x. All right, and that equals whatever is on the right. All right, so for this one, I want to rewrite it again, because in the denominator I have these two being multiplied together. So I'm going to write it again with a single fraction in the denominator. I'm not changing the numerator yet. So I have sine over cosine plus cosine over sine. Then my fraction bar. And the denominator, I'm going to multiply these fractions together. So 1 times 1 is 1. Cosine times sine is cosine sine. Oh, and it equals the right side. Okay, so now I I have a fraction divided by a fraction. So I'm going to multiply by the reciprocal so I can cancel out the denominator. So in the denominator, I want to cancel this fraction. So I want to multiply by the reciprocal. Cosine sign on top. And then the bottom is 1. So I just flipped it. And if I multiply, then those pieces cancel. And that's just a denominator of 1. But anytime if I'm changing a fraction, if I change the denominator, I have to also change the numerator. So the entire numerator is also going to be multiplied by cosine sine over 1. There are 2 parts to my numerator, so I'm going to have to distribute to each one of them and multiply. All right, so again, the denominator, I don't have, it's pretty much gone, so I don't have to worry about that anymore. Here, I'm multiplying fractions, so cosine sine times sine gives me cosine sine squared. And 1 times cosine gives me cosine, so over cosine. Plus, again, multiply numerator times numerator. Cosine sine times cosine is cosine squared times sine. And that is going to be over 1 times sine is sine. Equals the right side. Okay. So next, I have 2 separate fractions. Before I combine them, I want to simplify them. So I have, on this one, I have a cosine over cosine. That's nice, because now the denominator's gone. It's just sine squared. Plus, this fraction, I have a sine in the numerator and a sine in the denominator. That's also nice, because now that fraction's gone. That's cosine squared. And it should equal whatever's on the right. All right, so now, sometimes it's good to check what is it I'm trying to make it equal. 1. Okay, so I'm just simplifying this as much as I can simplify. That's what the 1 tells me. Sine squared plus cosine squared. I feel like I said that a lot, so that's probably on my formula sheet as Pythagorean identity. So I'm going to check it. My Pythagorean identity on my formula sheet that has sines and cosines in it is sine squared theta plus cosine squared theta equals 1. And look, that's the same. Sine squared x plus cosine squared x, that's the same as the left side. Again, I don't have to even rearrange anything. I can just pull this out of my problem because it matches the left side, and I can take the other side and put that in its place. So it's just 1. And I'm trying to say that it equals the right side, and the right side is 1. It was the same all the way down. So yes, 1 equals 1. It is verified.